Hello, everyone. Welcome. My name is Mike Zephyr, and I'm an associate professor in the Faculty of Business and Economics at the University of Melbourne. And this is our second talk by the Mplus team. Today, we've got Bengt Muthen here for our Quantitative Methods Network, or QMNET seminar series at the University of Melbourne for 2021. We're kicking off with these two talks in concert with the Melbourne Centre for Data Science, who is graciously co-hosted these sessions. And today, Bengt is going to be talking with us on some applications of latent variable modeling in Mplus. And I'm pretty sure that everyone knows who Bengt is, but let me provide you with an introduction in either case. So Bengt obtained his PhD in statistics at the University of Uppsala, Sweden, and is professor emeritus at UCLA and a co-developer of Mplus. He was the 1988-89 president of the Psychometric Society and the 2011 recipient of the Psychometric Society's Lifetime Achievement Award, and the 2017 recipient of the CELS Award for Outstanding Career Contributions to Multivariate Experimental Psychology. And I'm sure if they could give out that Lifetime Achievement Award twice, that you might get it a second time. But thanks so much, Bengt, for agreeing to do this and being here today, and take it away.
Thanks, Mike. This is great. So it's exciting to be talking to Australia. Good morning to all of you down there. And greetings from Los Angeles. We try to be geographically diverse because yesterday Tiemer spoke from Salt Lake City, Utah, and now we have Los Angeles, California, where we're heading towards spring, it looks like, slowly. So this talk then comes at a good time because we just released a new Mplus version earlier this week, version 8.6. So we're slowly inching towards version 9, which looks like it's actually possible that it might happen. There were, after all, 9 literal versions. So this is a talk that I built on several other ideas that I presented in different forums. It has 3 parts. First, you start with standard classic structural equation modeling. We're going to take a look at the Wheaton et al. Model from a different perspective, which is kind of exciting. And then we're going to talk about a new latent transition analysis model, and then turn to multi-level time series analysis of cycles. So 3 seemingly very different topics, but they have a common theme. It's the virtue of using random effects to pick up heterogeneity, especially the virtue of using random intercepts. So on slide 3, I want to advertise the new Mplus web talk series, which you find here at this URL. And I just recorded number 3, which is the first part of the talk today, although in a shorter fashion. And web talk 2 has to do with the second part of today's talk. It has to do with latent transition analysis and the new idea of random intercept latent transition analysis. And then at the end, web talk 1 relates to the time series modeling. And this talk then summarizes all of those in 1 hour. So instead of listening to 1 hour plus 5 hours plus 3 hours, so 9 hours of web talks, you got the bargain here to be able to get that information in 1 hour or so, maybe 1.5. But of course, if I go too fast, which is possible, then you also can always fall back onto these web talks. And more web talks are coming. We have a lot of ideas that we want to cover, Tiemer and I, and a lot of aspects of Mplus that hasn't been stressed enough. And we find that it's a quick way to communicate new ideas, particularly showing how you do this in Mplus. So let's start with this classic model. I call it a model of 1975, although it was published in 77 in this book series, Annual Book Sociological Methodology. Blair Wheaton, the first author, and I, we met in the academic year of 74-75 in Madison, Wisconsin, at that university. You get the long story of that meeting and that year in Web Talk number 3. In any case, I had just learned about structural equation modeling from Euroschool. I was fortunate to be in his first student group when he came back from the US to University of Uppsala, together with Dag Servom and others, or Folsom, for instance. So I learned how to do this kind of modeling, and Blair couldn't find a well-fitting model, so I suggested correlated residuals. That was a big innovation at the time, and the model fit much better. So here we have 3 time points, and we have 2 indicators per time point, anomia and powerlessness, measuring alienation at these different years, 1966, 67, and 71. And then we have a background variable, SES, an SES construct measured by educational attainment, and Duncan's socioeconomic index. So the contribution of this paper was estimating the stabilities here in the relationships between the constructs, controlling for background, and adding residual correlations. Now, the standard specification of this model then is that you would hold the loadings invariant across time. So you have metric invariance, and you would correlate residuals for each factor indicator at adjacent time points, at least adjacent time points. And we got this fit here. We get a 31 parameter model with a chi-square of 90 and 13 degrees of freedom. So it doesn't fit that great. Sample size is 932, but still, root mean square error approximation isn't that great. CFI is almost always happy, so I would say there's room to improve this model, but the many attempts that we made, Blair and I, led to just a more cumbersome model without really hitting on something that fit really that much better per parameter added. So now, 46 years later, I thought of a new model, and it has fewer parameters than the classic, but it fits better. Fewer parameters means more degrees of freedom, and still, that is a more restrictive model, and still it fits much better. The BIC shows it clearly. The likelihood is better, and you have fewer parameters, so BIC is much better than the classic. And root mean square error of approximation goes down nicely, and CFI is almost 1. So I thought that was worth talking about, and I want to make you curious now about what is this new model. So for that, I have to take a step back into a little bit of history of multi-level factor analysis. So at the top here, we have this decomposition of an observed Y variable for individual I in cluster J as a between part and a within part. 2 latent variable vectors, like Tiermer talked about yesterday. And for each part, we assume that we have a factor analysis structure, loading matrix, factor vector, and the residual epsilon for between and for within. And then you have a covariance structure that is the sum of between and within, and each part has a factor model structure of the usual kind, lambda psi, lambda prime, with subscripts B or W. So that seems to have started up in Stanford with Lee Cronbach doing his research on classrooms and schools. And he wrote this research paper, which has been quoted a lot without being published. And a fellow Swede came over there to Stanford as a visitor, Kjell Härnqvist, and was inspired and wrote a paper on this matter. Back then, there was pretty primitive ad hoc estimation techniques. Basically, the between part was estimated by using the means for each cluster, means of a school, or means of a classroom or a school. And that has deficiencies. So Harvey Goldstein and Rod McDonald moved to make both the model more general and start looking at more efficient estimation. And Rod McDonald and Goldstein wrote a paper then in BR, British Journal of Mathematical Statistical Psychology, looking at the likelihood. And I took an interest in that too in 1989, shortly after, where I wrote about latent variable modeling heterogeneous populations. Part of that, the ending part of that, had to do with multi-level factor analysis. And I applied that to data, educational data that I got at UCLA in Journal of Educational Measurement. And then there's this old paper, but seemingly quite useful still, an overview paper that gives strategies for how you find the structure on each of the levels. This was actually an attempt to do this in existing software, like back then, ListComp, before Mplus came. And actually realizing that for balanced data, you can do a two-group analysis and get maximum likelihood estimates. And there would also be approximate maximum likelihood estimates when you don't have balanced data. So the standard example here is students within classrooms or students within school and looking at achievement testing. And we note a couple of things then. There are typically fewer between level factors, FB, than within level factors, FW. And the interpretation of the factors on the two levels are quite different. So for instance, on within, you have math and reading skill factors, for instance, whereas on the between level, it just has to do with school excellence. So the meaning and the number of factors may differ. Now let's take a look at this in a little bit more detail. So if you write the two-level factor analysis model with only one factor on each level, so you don't have a matrix but a vector here, lambda b on lambda w, you could write this in a very interesting way in a two-level fashion, where level one has then this expression. Nu is the literal or y kind of notation, nu intercept subscript j, plus the within level part. And this is the intercept then, which is a random intercept, which on level 2 has a mean and then a covariance structure by having this between level factor analysis structure. So if you insert level 2 into level 1, you get the full expression up at the top. Now there are two key aspects to this then. One is that two-level factor analysis can be viewed as a random intercept model, where the intercepts have a factor structure. And they don't have to have a factor structure. It could be totally unrestricted if you want to. And second, because the random intercepts appear here in the measurement of the within level factor, you allow for a certain form of measurement non-invariance, differential item function, or item bias, so to speak. Which is kind of interesting to think about it that way. So let's try to express this in model diagram form then. You have then on level 1, if you start with that, you have the observed variable, and then we have a random intercept. We mark that by a filled circle here on those boxes. And then we have the lambda f structure down here, plus the residual epsilon wij. And on this level, you have then the random intercepts. They are latent variables, in this case 3, and then you have the factor structure up here. So there's a direct translation between the equations and the figure, and this is the way we do it in the user's guide, except we turn it upside down, so the between part is at the bottom, but it fits much better this way here. Sigma b from the level 2 and sigma w from level 1. Now it's interesting to go a little deeper into this, where we write the covariance structure for the students within school by displaying the data for each student. So we have the same model here. Now we're looking at it for school 1, students 1, 2, 3, and school 2, student 1, 2. And each of those students have a data vector, 3 variables in this case, observed. And each student has the same covariance structure, sigma w plus sigma between, for all the students down here, right? Same, because we assume they come from the same population. And then we have zeros here, covariance between students in school 2 and students in school 1 due to random sampling of schools. But in the off diagonal here, it's not zero. That is, within a school, students share the school contribution. So you get a sigma B contribution for all the off diagonals that is contributing then the numerator in an interclass correlation computation. Same thing for students in school number 2. And this is borrowed from this 1994 chapter. So if you look at it that way, if you look at this strung out data structure, which is how it's often portrayed in statistics or econometrics, but not usually in social science descriptions, we can actually diagram that as well. Let's take an example of 2 students for every school. So here's student 1, here's student 2. Both of them follow the covariance structure of sigma W. So we have equalities between the students for every single parameter here. And the 2 students share the same school influence up here, which has then these random intercept influence the observed boxes with unit coefficients, and they have the factor structure up here. So the covariance between the 2 students is due to them coming from the same school. That's the only connection between the students. So what are we looking at here? Is this still a multi-level model? Yes, it's still the model on slide 10. It's a multi-level model, except we have written it in a different way. We made a paradigm shift here. Did you feel it? What we've done here is express the model not in a 2-level analysis fashion, but in a single level wide fashion. We have 2 times 3, 6 observed variables here. So we write it out in a wide format, which you usually don't do when you have many students per school. You would get too many variables. But in this case, you have only 2. In fact, you could have a direct relationship between student 1 and student 2 if you had a small group research study where you have a leader and a follower, and the leader influences the follower. So that would give you a different covariance structure. Now we're talking about cross-sectional modeling here, students within schools. But the case of time points nested within individuals is also multi-level. So why not apply this thinking to longitudinal data? So then we just changed it to 2 time points, time 1, time 2, same student at the 2 time points. And we have the same equalities, and they correlate because it's the same individual. Correlate via these random intercepts, 1 for each observed variable, which we may or may not want to impose a factor structure on. Now, this thinking was actually, to a large extent, expressed by Ellen Hamaker in a paper in 2016 in NBR. And she calls it a CUTS model, Common and Unique Trait State Model. It's based on multi-level factor analysis thinking, but that one has fallen off the radar totally, it seems, and never been really applied in practice. It relates to latent state trait work that's been described in many articles over the years. And Christian Geiser now is perhaps the most recent contributor to that area. This is a book from 2020. So what we want to do is to look at a longitudinal factor analysis based on the multi-level thinking and just add this influence over time, which would be in the cross-sectional setting again, leader influencing a follower. But this is essential then. So it's extended to include auto-regression for the FW factors. So this multi-level based longitudinal model is quite different from the naive longitudinal model, which uses only the bottom part here, and then maybe throws in some correlated residuals. Here, the variables are allowed to correlate in a much more disciplined way, with fewer parameters. So going back to the Wheaton et al. Model, here's the classic drawing of the Wheaton et al. Model. So how would we draw it now, coming at it from multi-level factor analysis? Well, it would look like this. So you still have this part, 2 indicators of a factor repeated over time. But I'm making a distinction here between and within. And note that I'm still talking about a wide single level analysis. I'm just labeling it this way to make a distinction between variation across individuals, which is on the left, and variation across time, which is on the right. And note that the SES factor does not influence F1, F2, F3. It influences the random intercepts, one for each indicator. And here we have not bothered to add a between level factor for them. We just let them correlate. So we estimate the covariance and the two variances, and then the influence is 1 as before. And those random intercept factors are influenced by the SES. So that's the idea. Very easy to set up in Mplus, certainly. And that's where you get this much better fitting model. So despite using fewer parameters, it has better log likelihood, better BIC, and better chi-square, RMSEA and CFI. And on level 2, that is the variation across individuals, SES has a significant negative effect on the random intercepts, as expected. Increasing SES tends to make you feel less alienated, and that's the same in the classic analysis. But this now, looking at it from the measurement non-invariance point of view, this means that SES explains to some extent measurement non-invariance across people, which is represented by these random intercepts. Now on level 1, the within level, we have the dynamics of the persons. Positive effect of F1 on F2, but no significant effect of F2 on F3 from 67 to 71. And that's different from the classic analysis. Now you can try to improve the classic analysis, but looking at modification indices, but it becomes a much more cumbersome model. And whatever you do to it, you're not going to beat this big here. So that's topic number 1. And topic number 2 then is quite different in a sense. We're not going to work with continuous latent variable constructs, but categorical latent variable constructs. So we're going to touch on hidden Markov modeling and latent transition analysis. In hidden Markov modeling, we typically have only one outcome per time point. Here we have 5 time points. Hidden Markov tends to have many, many time points. Perhaps with applications like speech recognition, you have hundreds or thousands of them, and single indicator per latent categorical variable. Now in latent transition analysis, you have more than one indicator, multiple indicators typically, and typically many fewer time points, 2, 3, 4, 5 perhaps. Now the typical features of LTA, and this is the classic LTA, is that you formulate the measurement probabilities, probability of U giving C. U here, take the example of categorical variables, which we usually call U in the Mplus users guide. So we're talking about this measurement model, which is a latent class analysis for each of the 3 time points. And we typically assume measurement invariance across time so that we're dealing with the same construct when we look at the transition probabilities. So that can be tested, of course. And the second part is the initial status probabilities. And third part, then the transition probabilities, probability of moving from a class here to a class there, etc. Extensions then is that you add covariates, and they influence the latent class probabilities and influence also the transition probabilities. And here in version 8.6, we've added quite a lot of new features to make the interpretation of the output or the result analysis results more accessible. Quite a few features that are described in web talk number 2. You may be interested in measurement invariance across different kinds of individual groups. You can do multiple group analysis, but using direct effects from covariates has been found to be much quicker, as I demonstrate in web talk 2. Mover-stayer modeling is another version of this, where some people don't move from their initial class. So what's missing in these models then? Well, coming from the first topic to here, we recognize that we're talking about multi-level data. We have longitudinal data, time within person. So where are the random intercepts? Seems like if you have multi-level modeling, you should have at least have random intercepts somewhere. Perhaps random slopes too, but at least random intercepts. So that's a statistical perspective. We're looking at a multi-level model. Why not random effects? From a substantive perspective, you might be interested in traits. And these between level factors that I talked about can be seen as between subject differences that are stable across time. Stable across time. And from a psychometric perspective, you may think of measurement non-invariance, and you come at that from both the multi-level factor analysis perspective and the multi-level latent class analysis perspective. Now, in the mainstream statistical literature, random intercepts have been used for hidden Markov modeling. Here you have an example where you have this continuous latent random intercept that influences the outcomes with unit coefficients. As Altman is a lady who wrote her dissertation on this, I think, a very impressive piece in JASA. She's talking about multiple sclerosis patients, only 39 individuals, symptoms worsening and then improving. The outcome is number of lesions in the brain. It's a count variable, and T is 24 time points. And we have two latent classes, two hidden states, relapse versus remission. Now, this makes the estimation much harder. She did maximum likelihood, so she couldn't use the usual simplification of hidden Markov modeling, the backward-forward algorithms, because these observed variables correlate not only because of being influenced by latent classes that correlate, but also because of this random intercept. So this leads to a one dimension of numerical integration whenever you have count variables, certainly, or categorical variables, not when these are continuous. So given that, I thought there should be a random intercept latent transition analysis model, RI-LTA. So that's forthcoming in psychological methods. And here I have a version of that model where I have, instead of I have two indicators here for each of 3 time points. I could have had a random intercept for each of those two, like I did in the factor analysis part. That would lead to 2 dimensions of integration. So two latent variables, estimating their variances with unit influence. Instead, I put a factor behind and let the random intercept, so to speak, correlate due to being part of the same factor, but have different loadings between them for the 2 indicators. But then the loadings are invariant across time. So it is a random intercept factor in that sense. It's a trait factor in that sense. So you find the Mplus paper and scripts at this URL for that. Now, this can be time consuming due to this numerical integration, even though it's just one dimension of integration, because you need many random starts to be sure that you find the global maximum. The likelihood is a little bit more bumpy when you have this random intercept added. So in November last year, TMR worked hard on making speed improvements using a new 3-stage random start search that we came up with, and using specialized algorithms that draw on these old hidden Markov ideas. And that's described in this technical report, where we found a nice example. 20 hours computation in Mplus 8.3 can be done in 8.4 in less than 15 minutes. So that's a nice improvement. Now, my attraction to this is that RI-LTA fits much better than regular LTA for all the examples I've seen so far. It may change, of course, but I looked at 4 data sets from the literature. Life satisfaction in an LCA book by Hagenarst and McCutcheon. You see here, with only one more parameter, the likelihood is much better, the BIC is much better. And the mood data, 2 indicators, 2 more parameters for RI-LTA, much better likelihood, much better BIC, reading proficiency, much better likelihood, and much better BIC. Dating and sexual risk behavior, this is in the 2008 paper by Lance and Collins, where they introduced SAS-proc LTA. For 3 more parameters, you get a much better log likelihood, much higher, and a much lower, therefore much better BIC. We're going to take a look at the reading proficiency example. It has to do with the early childhood longitudinal study of Eccles K, measuring reading proficiency. 4 time points, twice in kindergarten and twice in first grade. And this has 5 binary items representing mastery of these different stages of reading. Basic reading skills of letter recognition, beginning sounds, ending sounds, so-called sight words, words in context. And the hypothesis is that this corresponds to 3 latent classes, 3 stages of learning: low alphabet knowledge, early word reading, early reading comprehension. And there's a covariate in here, poverty, having to do with the child's household income. And this is described by David Kaplan in this developmental psychology article. Now, if you compare regular LTA and RI-LTA, the first thing you would look at is the measurement probability estimates. So we're looking at the measurement model here. So just slowly saying this for those who are not used to looking at LTA measurement models. Classes are the columns, just like factors are columns for continuous factor analysis, and the rows are the items. So class 1 is characterized by mastering letter recognition, but having low probabilities of mastering anything else. Class 2, you can also do beginning words, and you have some good chance of mastering ending words. Class 3, you have add the probability of good probability, almost 1, to master sight words as well, and a 50-50 chance of mastering words in context. Now, if you compare that to RI-LTA, it's a fairly similar measurement structure. You have the high probability here, you have the high probabilities here, and you have the high probabilities here. There are some minor differences. This is a little higher here than there, and this is a little higher than over here. But substantively, you would make the same interpretation of the data. That's looking at the measurement model. Now let's look at the class probabilities. So you have here the 3 classes over the 4 time points. So according to regular LTA, there are about 70% in the lowest class in the fall of kindergarten and 81% at the end in the highest class. RI-LTA is a little bit more pessimistic. It says that 95% are in the lowest class in fall of kindergarten. And more optimistic, 97% have reached the highest level by spring of first grade. So there's a difference here. Now, what about the transition probabilities? You have then this transition from fall K to spring K, which is just one of the 3 transitions that you can have with 4 time points. So regular LTA, if you start at the lowest class, you have a 34% chance of staying in that class and a pretty high percentage of moving on to class 2. Now, if you look at RI-LTA, it says that it has a more optimistic picture. You have a lower chance of staying in class 1 and a higher chance of moving on to class 2. So once again, a little different in the interpretations. And again, RI-LTA fits the observed data considerably better. Now, then you have the latent class modeling with covariates. Say you add a covariate here, X, that influences the probabilities like this, and by influencing C2 and C3, you also influence the transition probabilities. Actually, 3 types of models often overlooked here, and I suggest they're in the web talk too. To first do a C1 on X to see if this covariate is important in the model. And then you can have C1 to C3 on X. That's a main effect model. In the user's guide, though, we try to be very general and have C1 specific C2 on X, C2 specific C3 on X. So you have an interaction model. That is, the influence of X on C2 depends on the C1 classes. So C1 and X interact. And that's a complex model that you don't often need to invoke to fit the data well. So you should test these models and look at log likelihood chi-square differences between them and settle on the model without not jumping straight to the most general model. Now, what does this look like in RI-LTA? Well, let's see. RI-LTA has this random intercept factor, as we talked about, and X then, main influence of X is to the random intercept factor, very much like we did with the random intercept model for the Wheaton data. So that is the main influence. But of course, for say a covariate like poverty, there could be differences in class probabilities and differences in transition probabilities as well. So what I've found here that there are a series of advantages of RI-LTA over regular LTA. Typically much better fit to data. More information is extracted from the data. We get to know about this random intercept factor. And in this example, the reading data example, there's less concern about the need for measurement non-invariance across groups of individuals, because the random intercept factor picks up on the measurement non-invariance that is constant across time, that trait, a feature of the random intercept factor. That one I don't think will hold generally for all data sets. And in fact, in the forthcoming Psych Methods article, where I analyzed the dating data from Lanza and Collins' article, this did not hold. There was measurement non-invariance also for the RI-LTA version. Now, there's less concern about the need for indicator-specific residual correlation across time. Now, backing up, regular LTA typically don't even bother to investigate residual correlation across time. But it is possible, and we have a paper on that, Timur and I, on how to model that. And very often in regular LTA, and these 4 examples that I looked at, there were indicator-specific residual correlations. But that was taken care of by RI-LTA. So you didn't need those residual correlations once you included the random intercept factor. There's also less concern about the need for lag-2 modeling, because you let the observed latent class indicators correlate not only through the latent class variables, but also through the random intercept factor. So the correlation between time 1 and time 3 is captured to some extent by the random intercept factor. You don't need to have C3 on C1, but you can say C2 on C1, C3 on C2, and that will be fine. So that's what I found in these data, and also less concerned about the need for mover-stayer modeling, because once again, that random intercept factor tends to, by high or low factor values for individuals, tends to capture a bit of the flavor of movers versus stayers. Now, the disadvantages are, of course, that it requires longer computing time, but things are going faster and faster. And it requires somewhat larger samples. And unless you have good sample size and clear class separation, 2 time points is not as easy to estimate for a given sample size as it is with regular LTA. Then again, if the RI-LTA model is the correct one, it doesn't matter if regular LTA is easier to fit, because it will give biased results. All right, so that's part 2. Now for something quite different looking. Multi-level times. Yeah, go ahead.
Sorry, we have a question here from Chris Martin, and I think this is about the categorical nature of LTA and maybe the advantages of that over models that work with continuous, perhaps observed and latent variables. And Chris asks, is there an advantage to modeling student progress using LTA when it could be modeled using linear variables?
I think you want to contrast those kinds of models. And in fact, in Web Talk 2, for this data set, I go through a model that has continuous latent variables instead, much like the model I used for the Wheaton data. And for this data set, it actually fits better. But that's not generally true. That's not universally true for the other data sets that did not hold. The advantage here is that you have a research hypothesis, a conceptualization about the substantive phenomenon, but you want to look at progression over stages. So therefore, you want to look at latent classes. If you had a continuous factor here instead, then you would have to, after you fit the model, go back and try to figure out what the stages would be. And that gets a lot more complicated. But I think you should try to apply, for data like this, you should try to apply both kinds of models. The models in my first part, longitudinal factor analysis type of model, and this model in the second part. That would be my answer. Should I go on?
Sounds good. Thanks.
So now for something completely different, but with things in common with the previous 2. And I should say that we're going to talk about cycles, we're going to talk about interventions, both propensity scores and randomized interventions. So now we turn the question around. This is the question I posed in Web Talk 1. I talked about what multi-level modeling can teach us about single-level modeling, and we saw that in the first part, dealing with the Wheaton model. But now we turn it around. What can single-level modeling teach us about multi-level modeling? Well, here we have, once again, the random intercept factor-looking model, except now we have continuous variables here. So it's no longer latent transition analysis, but it is multi-level factor analysis or longitudinal factor analysis model. So the question is, how do you analyze relations between variables at different time points using 2-level modeling? You know, 2-level modeling typically don't have these paths in it, but we want to know about them. So then I think time series analysis is perfect for that. Multi-level time series analysis, where time is nested within the individual. And this is what Tiermer talked about yesterday, dynamic structural equation modeling of the DSEM or the residual DSEM kind. So if you look at, for instance, an example of dynamic factor analysis, the single level wide way of writing it is a single level wide, 1, 2, 3, 4, 5, 6 variables, 6 columns in the data. That gets translated over into this situation on within, that is a factor within a time point t, regressed on t minus 1, and it has 2 indicators, y1 and y2 at that t time points. There are 2 indicators per time point. So the data would have 2 columns instead of 6. And then you have these random intercepts here for the observed variables once again, and they turn into continuous latent variables on the between subject level. And you can put a factor structure if you want to, but it doesn't make much sense when you only have 2 indicators. So the idea is that the DSEM data are in long format. So you have 2 outcomes per time point, resulting in 2 columns of data, not 2 times t, not 2 times 3 here, 6. And the across time effects is specified by using these lags notation, FW and FW with 1 lag. So this t minus 1 in this case. So this is quite a big step forward. And it's very suitable for intensive longitudinal data, where you have frequent observations, large T, 15 up to 1,000. Tiermer talked about daily diary data, but we also have ecological momentary assessments, experience sampling methods using wearables. So the within level is time, between level is individual, and the variation in within level parameters can now be expanded because we have so many more time points. We can estimate these param variation across individuals by many random effects, not only the random intercepts, but also random variance, random autocorrelation, random slopes, and random amplitude, as we will look at now. And that modeling with a large number of random effects is made possible by the Bayesian estimation. It would be impossible with ML. So Tiermer took the lead in writing that paper here in 2018, and Ellen Hammacher took the lead of writing an application in MBR. And Schultzberg and I looked at what kind of number of subjects and time points are needed for various variations of more or less complex time series models. And then Dan McNeish and Ellen wrote a nice Psych Methods article, a primer on two-level dynamic structural equation modeling, and many more references, and also short course videos. Topics 12 and 13 are at that web address. So modeling cycles, you can do that many different ways, dummy variables, splines, sine, cosine. So here you have cyclical behavior over time. I think this has to do with heart rate. So we have biological cycles, behavioral cycles, environmental cycles. And if you work with sine cosine, and that's an interesting kind of model, the function then is a trend that is cycling up and down across time. And you do that with the help of the sinus and cosinus functions. So you can think of this as a regression on two x variables that are computed and are a function of t, the time point, and with slopes that have to do with different aspects of the curve. And those slopes, beta 1 and beta 2, can be explicated or interpreted into amplitude, the height of the fluctuation, and into the phase. Now, the issue is here that we would like these slopes to be, or these amplitudes and phase to be varying across individuals. And right now in Mplus, we cannot have random effects in non-linear settings. They have to be in linear settings. Beta 1 and beta 2 can be random, but not amplitude and phase. So there's a way around that, though, that I'm going to describe. And I'm going to use that with, let's see, how do I get rid of this at the top here? No, it doesn't matter. This is from a study designed to detect at-risk mood profiles related to depression in adolescents. And it's ESM questionnaire measuring positive and negative affect in Dutch adolescents. And you have 200 individuals, several measures per day for 7 days. So that's in Frontiers of Psychology. So you have this positive affect variation across the day and the next day and the next day. This is Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, Monday. So if you fit that, you do that pretty well by this sine-cosine function, except you have a little bit of deviation here. Here you come to, let's see, Tuesday, Wednesday, Thursday. This is Friday. People get more positive about things in life. Friday, hopeful about the weekend. And here on Saturday, and a little bit on Sunday too, but then you're back to the doldrums here on Monday. And these are the low points, only a few of them. It's just before they fall asleep, they feel not so positive sometimes, I guess. Some of them don't. Now, this is an interesting little function that these are the observed averages across individuals, the red ones. But you can now, in Mplus version 8.6, you can insert a loop plot. So you can have a loop plot in the model constraint and get the estimated curve plotted in here. But to fit these data really well, we would want the dummy variables added for the weekdays, or at least for the weekend somehow here. And it's interesting, you also have a measure of tiredness, positive affect up here and tiredness. And it looks like when the positive affect, or when the tiredness it goes down, the positive affect goes up, and vice versa. They're inverse related to each other. So I did a cycle analysis of positive affect and tiredness, and I wanted to relate positive affect to tiredness. At least I wanted to relate the random effects of them to each other. And to handle this issue about random effects that appear in a nonlinear fashion in the model, I do a two-step analysis. And Tiermer and Mike talked about that a little bit yesterday. In step one, I do a two-level RDSUM, residual DSUM based analysis with random effects for the intercept, the level, sine-cosine slopes, that is the beta 1, beta 2 I talked about, weekday slopes, I had all of the weekdays, residual autocorrelation, and residual variance. And this is a bivariate analysis. You have positive affect and tiredness in the model at the same time. So that's a two-level model. And then I ask for plausible values. That is, I draw factor scores essentially, repeatedly, as you would in a Bayesian analysis. 200 of them, 200 data sets to capture the imprecision in the random effect estimates. Not only the point estimates that you get with factor scores, not even just point estimate plus standard error, but you get the whole distribution. Step two, then I used type imputation data for a single level analysis of those 200 data sets. And in that, I have a defined statement that transforms sine-cosine to amplitude and phase using the formulas I showed you previously. And then I regress positive affect effects, random effects on tiredness, random effects. Thinking of tiredness as the driver of the positive affect to some extent. And that uses a new Mplus version 8.6 feature, which is Bayesian estimation for type imputation. We didn't have that before. Didn't allow for Bayesian estimation. But that's beneficial because you can then automatically get the non-symmetric confidence intervals, which you get out of Bayes as a standard called credibility intervals, actually, for imputed data as well. So that's a new feature that's described in a technical appendix. If you go to Mplus version history page, you will find it there, and you can also go to the technical appendices part of the website and find it there. And we do find significant effects here. The level of positive affect is negative related to tiredness level. The higher the tiredness level is, the lower the positive affect level, which makes a lot of intuitive sense. But the amplitude, the fluctuations of positive affect is also positively influenced by the tiredness level. So the more tired you are on average across time, the higher the positive affect amplitude, the variation in it. So that takes a substantive researcher to explain why that might happen. And the residual variance is also positively related to the level of tiredness and to the tiredness residual variance. And I'm talking about random effects here and results from the second step. I thought it was kind of interesting and providing a simple way to handle this kind of a model, which is often used in statistics, for instance, in sleep data and other situations. It's called a cosine-norm model. And you don't have to have just one sine-cosine curve that has 24-hour distance, but you can also have several of them. You can add several such components. So you can have actually 4 x variables instead of just 2. Now here's a Totally different example, very long longitudinal data. T is about 1096. So this comes from an electricity application where firms are the unit. They're measured daily over 3 years. So 3 times 365 is approximately that much. And it was an intervention, change in tariff, and 184 firms in the intervention group, 800 in control group, not used here on this page, but used in the paper. The pre-intervention data is 1 year. So you have 1 year of electricity data, and the post-intervention data is for 2 years. We do a Sine-Cosine model here, using cross-classified instead of the two-level model that Tiamat talked about yesterday. So what you show here is this bar here, vertical bar, is when the tariff change, the intervention happened. So we see then that the amplitude, this on the right of this, in this picture, shows what would happen if there was no intervention. But to the right of the line on the right shows what happened after the intervention. Much lower amplitude there. So if you piece the first part here together with the last part, you see that you have a positive effect, or an effect of lowering the amplitude by this tariff change. Here is what would happen if this treatment group did not get the intervention. And here we see what the treatment group would have been before the treatment started if they had the treatment already then. So it's like this is forecasting, this is backcasting in a sense. Now, this is no randomization here in this example. So Schultzberg then wanted to match on propensity scores obtained from this rich pre-intervention data that he summarized in random effects to evaluate post-intervention outcomes. So he has a time series model down here, YT, I should say T minus 1 here and T here. And on the between level, you have all these filled circles. On the between level, you have random effects here, just 3 random effects in this case, which influence being in the treatment group or not. You know, this is the propensity score idea. So the propensity score estimation is estimating or predicting a binary outcome on the between level by random effects, latent continuous variables. So then you get the propensity score, and then you match on those propensity scores to evaluate the intervention. So that's kind of a nice application of DSEM or RDSEM. This Schultzberg is actually an interesting guy. He's my nephew. And here we are together at in the corridor of the Department of Statistics at Uppsala University. If you look carefully, you see that's me in 1977 with a wreath and a tuxedo and all. And every graduate gets hung on the walls here in this corridor. So this fellow, that was 2016 in this picture, but in 2019, he got his PhD in statistics. Kind of an unlikely family affair. And he's now working as a chief statistician at Spotify in Stockholm. So kind of an interesting turn of events. Now, here we have a randomized study where we can then consider, if you just look at the picture first, we have time series data before an intervention and after an intervention. And we have random effects that are the predictors and random effects that are the outcomes. And then you have a treatment variable on between. This is time on within, people on between. And we say that the treatment influences, we capture the time series by random effects. So treatment influences these random effects. And you have an interaction between treatment and what the random effects were before treatment. So these are moderators of the treatment, and the outcome are latent random effects. So do these data ever happen? Yes. I have these data. This is another Dutch study, have to do with positive emotions in the Journal of Consulting in Clinical Psychology. Experience sampling method, 60 time points before treatment, 60 time points after. Each period has about 10 beeps per day via digital wristwatch. sample size is a little over 100. So here you see those daily cycles again, captured by the Sine-Cosine curve with random effects. Now, then you have this situation here where you have potential interactions of treatment with the pre-intervention random effects. And the preliminary findings for intervention effects on the random effects on the post-intervention time series, positive effect on the level, that is a level post, and higher effect on level for persons with higher pre-intervention level. So if they have higher pre-intervention level, treatment interacts with it to give an even higher post-intervention level. And you have a positive effect on level for persons with high pre-intervention autocorrelation. So high pre-intervention autocorrelation influences this. Interesting, once again, the concept of autocorrelation playing a substantive role that Tiermer touched on yesterday comes back here. Finally then, I want to mention, I'm not going to treat that topic today, but the Mplus Users Guide has gotten a companion, as you might know, regression and mediation analysis using Mplus. And we wrote that book mainly because so much had happened in the mediation area. So here's the table of content where you have starts off with linear regression analysis, classic mediation analysis, and then comes down to causal inference for mediation using the new thinking of counterfactuals that many research, including Pearl and Vanderweel and Robbins, have promoted. And then I go into talking about categorical dependent variables, count and sensor dependent variables. And for all of those cases, you need new kinds of indirect and direct effects definitions. So you talk about mediation with non-continuous variables, and you have so-called counterfactually defined effects. And that was introduced in Mplus a couple of years ago. And I recommend that you, if you're interested in mediation modeling, you take a look at this. There's also a good chapter on Bayesian analysis and an interesting chapter on missing data with modeling that I haven't seen elsewhere. Particularly the combination of Bayes and missing data comes out to be quite interesting. Finally then, here's what we have in recent papers. You find them under recent papers. That's a overlooked part, I think, of our website, where we list the recent papers. It's towards the right in the home page. Well, you can take a look at it if you want. Oh, maybe not. Not supposed to go there. Doesn't want to go there. Okay. Anyway, so we have a series of papers recently here, starting with the testing of nested models, and then going into the centering that Tiermer talked about yesterday, and then making variable interactions using Bayes, and then advances in Bayesian model fit evaluation and comparison of models for analysis of intensive longitudinal data, and expanding Bayes for loaded. And finally, we have Bayes for loaded, so you can have odds ratios for binary outcomes also with Bayes, which used to be only probit before. And then we have the negative binomial for count variables, and negative binomial is one very flexible count variable model. Another recent model is by Evan Hammacher and I on the fixed versus random effects debate in panel data and how it relates to centering and multi-level modeling. That's in Cyclic Methods, very accessible. And then this paper that I talked about, which is a latent transition analysis with random intercepts. Now, if you're interested, we do have some time. We could take a look at this run that I did, the two-step run. So here I'm looking at HTML output, where you have all of these different sections. You know, you have you can ask for HTML output, and then you can skip or jump between sections very easily. You can magnify this here. So what I did here was look at a two-level random model with estimator base and with at least 1,000 base iterations with thinning. So there are many more iterations that are done, but we only record every 10th. And I use proc equals 8 for it to go faster. And then on the within level, I have quite a lot of random slopes. SPA is the positive affect. X1 is the sinus part of the sine-cosine, and X2 is the cosine part. So those are random. And then I have weekday dummies, and each of them gets a random slope. And then I have RDSEM, that is, I look at the residual of positive affect, outer rest on the residual at the previous time point. So the hat is the RDSEM notation. I look at the residual because we have this regression on X1 and X2 on the weekday dummies. And what I really want then is to correlate the rest. So it's a little bit more like, I would say RDSEM is a little bit more like regular multi-level modeling, whereas DSEM has to do with the dynamic part, where there's a direct influence over time between the outcome variable. Here it's instead regressed on a set of variables that create a curve shape over time. And here's a random residual variance, which we have introduced recently. And then the same thing, the whole same thing, all of these random effects for the second variable, tiredness. And then on the between level, I let all of those random effects be covariate and estimated, means of covariance is estimated freely. So no structural model here at all. And then in model constraint, I plot the estimated curve by a loop plot where I use the sine-cosine function for with the labels of that I put in up here, and rather up here, and for both positive affect and for tiredness. And then I asked to get all the factors and save 200 of them with thinning of 10. So outcomes then, well, I could actually do this. I'm in the way here. So at the end, you get all these values saved. And these are time invariant covariates, age and gender, etc. And then you get all of these random effects saved here, which you read in for a second step analysis, which is then single level, and you regress the random effects for positive affect on the random effects for tiredness in this case. So that's, I think, that two-step approach. We were talking about that today, Tiamer and I, how good it is and under which circumstances it would compete with the real thing, that is allowing for random effects for nonlinear functions. If one day we have a lot of those applications, we may program it. But for now, we don't think this has much of a drawback of doing it this way. There are questions still remaining when you do this imputation from the random effects model. Should you bring in the covariates on between here, for instance? Should you bring them into the model to improve the random effect estimation and the plausible values? But Tiamer was saying with many time points, it's not going to make much of a difference. And this is a general question that's come up in other contexts too. If you bring in covariates that are part of generating plausible values, and then you do a second stage analysis, will you create biases? This has come up in the US context, educational testing, using the so-called NAEP data, National Assessment of Educational Progress, the nation's report card. It's one big mimic model where you have a bunch of covariates, and then you have the unknown ability or achievement, continuous latent variable factor. And then you have indicators. Since you have few indicators for any one person, you draw a lot on the covariates. So the question then is, once you have those plausible values for ability or achievement for that factor, and regress that in a secondary analysis on covariates, when and why and will you have biases of some kind? So we're talking about that, Timur and I, maybe we need to do a paper and study this in a simulation study and see how that turns out. So with that, I think I am done, and we are getting shorter on time. So I'll stop there.
Thanks so much, Bengt. That was great. We've got a question here just about some of the online materials that you might have. And Craig Sewell is wondering if your analysis of positive affect and tiredness cycles is published anywhere or accessible.
It is not. It's lying over there on the desk of projects in progress. but I figured that I'll get to it right after this event. When I have this behind me and the web talks behind, the first 3 web talks behind me, I have time for that. So that'll be next. Yeah.
It's interesting research. How about anyone else? You can type your questions into the Q&A or raise your hand, and I can bring you into the session and unmute you. So don't be shy. Or be shy but brave. That also works.
Yeah. Or instead, listen to the web talks and get more details about it there.
Right. Right. Maybe I could start off with a question about this kind of 2-step approach with DSEM specifically, and then using the new imputation option with the generated plausible values. So when you're using a kind of DSEM lagged specification, does Mplus also generate plausible values for the lagged variables, or in order to get those, might you need to put a latent variable behind the within part of the observed variable?
Okay, that sounds like a perfect question for Timur.
Yeah, can you guys hear me?
Yeah.
Well, in general, if you're talking about observed variables, then all you need is really the between part of the variable, and if you subtract that from the observed value of the observed lag value, then you get the imputed value for the lagged portion.
Even for the first occasion?
Yeah, well, yes, even for the first occasion, yeah. So, well, actually, the situation with the first occasion is also always a little more, is a little trickier, actually. But generally, for after the first occasion, yeah, will be just that. Yeah, with the first occasion, we sometimes use this sort of kind of averaging, and I'll have to look at the specific model to give you more details about what exactly happens there. But actually, I had one thing I was going to mention on the earlier question. Was about the mixture models and why we don't use a continuous variables. And sometimes, the issue is there that it is actually the answer is sort of substantive. And if we believe that if the subject of study is such that the student will acquire a certain ability to read faster or comprehend faster, and it's more like of a discrete kind of a change. All of a sudden they didn't know how, they barely were reading, and all of a sudden they're a smooth reader. And so, substantively, sometimes people believe that latent transition analysis is better than actually continuous variables. And, if you actually can get something out of this talk that Bengt just got, and I thought that this is actually was the main thing that I got, is that these substantive ideas that you kind of, you actually, if you listen to the substantive ideas, that will lead you to actually to the right model. And for example, if you have, in multi-level factor analysis, right, we could have actually used some kind of, factor analysis that includes all the variables in the classroom, all the students, and then kind of come up with these factors on the between level and stuff like that. But we don't, right? We actually do a more structured two-level approach, and that's because this substantive idea that we have a effect from the individual and effect from the cluster, that sort of substantive idea is really what simplifies the model and actually captures all the correct the correlations in the data. So
it leads to an interesting question, I think. So say that the substantive idea is this transitioning between very discrete states, but a continuous model with continuous latent variables fits the data much better. Are we allowed to use this model, the discrete model? I mean, is it kosher to continue with a model that is not the best fit to the data? Sometimes not by far. So then that leads to the question, if you have those research questions about discrete development, but the data are best fitted with a continuous latent variable, can you use the continuous latent variable model to get to interpretations and results that corresponds to the original research question? And that's interesting. Once again, that goes back to that nation's report card that I mentioned, where they have a continuous factor, but what they report are these 4 proficiency levels. So at the end, they go back to a discrete interpretation, and they do that by having anchor items that really clearly substantively define that you are at a different level of understanding. But I think that's an interesting question. Are you allowed to use a model that can be beaten by another model? And if so, for what purpose?
Yeah, I think that gets probably a lot more air and leniency in the forecasting literature, where they're quite happy in certain cases to have a poor fitting model if they think that improves out of sample predictions, right?
Right.
It's interesting.
Yeah, that's in the prediction area. And here we're more interested in the explanation, I think.
Right. That's exactly right. So again, feel free to use the Q&A function or put up your hand. If you want to raise your hand, there should be a button on the very bottom. Or maybe you have to go into a submenu there as a guest. I'm not seeing what everyone else is seeing. You brought up something interesting, and that was whether or not to include predictors when generating plausible values. And I was wondering if you could draw a kind of analogy to the case of finite mixture modeling and latent class analysis. When I know 10 or 15 years ago, the procedure was based on some of the work in that Hagenar's and McCutcheon book to just include any outcome of a latent class in the model, but then it acted almost like an indicator of the classes, and then they adopted more recently and in Mplus as well, kind of a multi-step approach. So you can get information about the classes and use that to predict the outcome. And I was wondering if that was a kind of analogy that you might draw, or if instead you're thinking about the generation of plausible values on different terms.
Yeah, when it comes to this model, and so you're talking about, say, a distal outcome out here, which becomes like another indicator.
Right.
But I guess Tierman and I think that the three-stage methods for doing that, handling a distal outcome, are okay. But when you have a covariate here, three-stage methods have a problem, I think, when there is measurement non-invariance with respect to x.
Right.
And you have a poor measurement model here that is with low entropy. It gets thrown off by including the x variable. That could be a sign that you have measurement non-invariance, so you have direct effects to the indicators. So I go through that exercise for the reading data. I don't know quite how that would translate to that two-stage procedure I talked about, but it is certainly related. Yeah, it's a good angle to think about it, I think.
We do actually talk about this in an imputation note bank. So we've actually documented this. Actually, I believe that was the first place we actually saw this, where bringing in a mixture model and try to impute the latent class variable, you are better off having the covariates in. So there's a substantial improvement of the. So we have the document in terms of the Bayesian imputation of the latent class, which was, I think Mike was referring to. So that's where we actually have the idea that, in fact, but again, you know, in these multi-level models, it's maybe not as important. Where in mixture models, it's very direct. So there is a substantial improvement, but I think that in multi-level models, if you have like the twin-level covariates, they're not as important because within the size of the cluster will really dominate the distribution of the random effects, and the predictors on the between level are going to have a minuscule impact. But in mixture,
yeah. So just to be clear, so Tierma agreed that if you have an x variable here, you're better off including that together with the Latent class indication, not do the analysis of this first and then that. It can be dangerous when you have poorly defined measurement models and direct effects. But if you have, say, a distal outcome here, the three-step method seems to work quite well.
Right. And maybe some of those, the multi-step procedures, especially when everything is latent and you get high dimensions with ML, it sounds like you've resolved a lot of the computational issues. If you can do in 15 minutes what used to take 20 hours.
Yeah.
Okay, great. Should we, oh, here we have a question. Okay. So, Young Sios asks, the idea of putting outcome variables when estimating plausible values seems interesting, but it appears counterintuitive and also considering LTA with distal outcomes. Any thoughts? Any thoughts? You must have been typing that while we were.
Wait, say that one more time.
Sure. If you click, I think at the bottom of your screen, you might have a Q&A button and you can see it too. So it'd be
Q&A
and
at the top of my
answered.
screen
And, oh, okay. And then down at the bottom, starting with the idea of putting.
No open questions, it says here.
Oh, sorry. I clicked answered live. So now it's under answered.
Oh, okay.
And then it would be.
The last one.
Yeah, that's right.
Counterintuitive and also considering LTA with distal outcomes. Well, the plausible values are driven by the relationship of the outcome variable on predictors. So you must have an outcome variable to be talking about random slopes. So I don't quite see the connection between that and LTA. Yeah, I don't quite see it. You know, in this analysis behind here, it's regression of two variables on the sine-cosine x and x1 and x2, and those give the random slopes that we're talking about estimating possible values for. So I don't know how that would translate to LTA with the distal outcome, but maybe that's my shortcoming, not the questioner's.
I've allowed young CO, if you want to unmute yourself, you can clarify if you want. There's no obligation, of course. Might be having a technical issue.
Yeah.
And we have another open question.
I should add, though, that regarding plausible values, you can actually get plausible values also for latent class variables, not only for continuous variables, continuous latent variables.
Right. Oh, I am in a loud spot. No problem.
Okay.
Okay, great. Well, there are also the web talks that Bengt mentioned, and all of those great papers that can be found through the statmodel.com website.
And I would say that if you have suggestions for topics that you think would be important for web talks, we're interested in doing them.
That's great. It's certainly in the age of Zoom and kind of lower CO2 emissions.
Right,
with less flying. That sounds fantastic, and obviously you and the Mplus team have set up some fabulous resources for everyone to access and freely access, which is of course of great benefit to everybody across the globe. So thank you so much, and we really appreciate this, and thank you, Young CSS. Thank you so much for sharing your thoughts. So this will be posted on the QMNET YouTube channel, and we hope to see you again soon.
All right. Well, thank you very much for listening, and thanks for arranging this, Mike.
Pleasure.